Hi everyone, this is the first video in a series I'm doing on matrices, which ultimately has a focus on reviewing and understanding matrix multiplication. In this first lesson, what we're going to do is get comfortable working with matrices and vectors so you can see the topics that I intend to cover in today's video. We'll cover what a matrix is, the basic operations we do on matrices. Throughout the videos, I'm going to introduce in special named matrices, so we will see our first group in this video. And then somewhat unconventionally, I want to conclude by identifying vectors as matrices of a particular form. In all of the videos in this series, I will drop in some exercises along the way. Well, let's start with the basics. So a matrix is a rectangular array of numbers. Typically, to name matrices, we like to use capital letters. For me, capital A is the most common. If I need a second one, it might be capital B. You might also see capital M and N. Since a matrix is a rectangle, it has a certain number of rows and columns, and we always provide the row and column number in that order. So an M by N matrix has M rows and N columns, and you'll hear that I'm really trying to over-enunciate those letters because M and N sound similar, but those are typically the dimensions that we provide. And the notation that I'm using here on the third line, you can read that as A is an element of the set of M by N matrices whose entries are real numbers. So that R to the M times N denotes the set of M by N matrices of real numbers. And that will be the focus of our study over the next several videos. Sometimes we will want to work with the entire matrix at once and we will just say capital A, otherwise it might be advantageous to think coordinate-wise with the matrix. So entry notation, we often will use little a sub ij to denote the entry in capital A, which lives in the ith row, jth column. For example, in this matrix that I've put here at the bottom of the slide, little a sub 2, 1, the 2, 1 entry in this matrix, is the entry that you would find in the second row, first column. If you want to think entry-wise, but in a way which is more concise than what I've listed out, sometimes we'll just say the matrix of entries A sub ij, and you may want to add to that the row index I goes from 1 through M, and the column index J goes from 1 through N. Or it might be enough just to say, hey, this is the matrix of entries A sub ij, which is what I've done on the right. Quick remark before we move on, we're often interested in matrices which have the same number of rows and columns. We'll call these matrices square. Let's cover some of the basic operations that we perform on matrices. The first is scalar multiplication. So given some matrix A, you can scale it by the number lambda. Just a plain old real number like this, we will often call those scalars. So in this example I've put up here, A is a 2 by 3 matrix because it has 2 rows and 3 columns. The scalar is the number 2 in front. And to scale this matrix by the number 2 means to just go entry by entry and multiply each of the entries individually by 2. So you can see the row -1, 0, 5 became the row -2, 0, 10, and likewise the second row 3, 5, -4 became 6, 10, -8. All matrices can be scaled. Our next operation though is addition, and that is only defined between matrices which have the same dimension. So here, I can add these two matrices together because they both have dimensions of 2 by 2, 2 rows, 2 columns. Addition also proceeds coordinate by coordinate. So you can see the sum of these two matrices was formed by adding their respective coordinates. The last operation I want to look at for general matrices in this video is how to compute the transpose of a matrix. All you do is you just interchange the rows and columns, or basically you flip the matrix. What I'm going to do is take the first row, 1, 1, 6, and make that the first column. Similarly, the second row, 7, 2, -1, became the second column. From the other point of view, the first column of the original matrix A, 1, 7, became the first row of a transpose. Okay, so here's our first quick exercise, just making sure you understand indexing. What entry is in the 3, 1 position of a transpose? The answer is 6. Two different ways you could have done that. Looking over at the matrix on the right, if you go down to the third row, first column, we see a 6 there. Or you could look back at the original matrix A and recognize that the entry in the first row, third column, the 1, 3 entry, should become the 3, 1 entry after we compute the transpose, and that is correct. So if you think of this matrix A as consisting of a bunch of coordinates of the form A sub ij, The transpose is the matrix which consists of coordinates corresponding to the original A sub j i's. This is this remark I've put over here on the right. We will use the traditional notation of capital T to denote the transpose. It's possible to see other notations. For example, in the program MATLAB, transpose is denoted with a single apostrophe, but I will stick to capital T. Some matrices come up and have special names. So the zero matrix, which we will write as boldface 0 sub n times n, where that's the size of the matrix, is simply the rectangular matrix where all of the entries are 0. So it could be square or it could be rectangular, but you can think of it as the additive identity for the set of matrices with the same dimension. The identity matrix, on the other hand, is always square. So I will simply write I sub n to represent the identity matrix, which is n by n. The identity matrix has ones on what we think of as the main diagonal, which starts in the top left corner, and zeros everywhere else. So here I've put the 3 by 3 identity matrix I sub 3. Two more ideas I want to introduce here. We say a matrix is symmetric if it is equal to its own transpose. For example, if you take this matrix A, which is 2 by 2, and flip it over the main diagonal, you'll get back the same matrix. On the other hand, we say that a matrix is skew-symmetric if, when you compute its transpose, it's equal to the original matrix times -1. I didn't put an example here. Instead, I'd like to ask you this question. If A is a 5 by 5 matrix of real numbers, which is skew-symmetric, what can you tell me about the entry in the second row, second column? Okay, the answer is 0. So all of the elements along the main diagonal, including A sub 2, 2, are left where they are, and yet for the matrix to be skew-symmetric, they must be equal to negative themselves. The only number that satisfies that x equals negative x is 0. So the main diagonal of a skew-symmetric matrix is all 0. Okay, that was a quick exercise. Here are some others. Suppose that lambda is a real number, so you can think of that like a scalar. And first, let A and B be m by n matrices. In other words, they have m rows and n columns. Take a moment to compute each of the following. So for 1 through 3, I mean, expand them so that you've removed all of the parentheses that you see. For this first one, if we take A and we flip it, and then we flip it again, we're going to get back the original matrix. If you'd like to, you can do that in coordinates. So if I take A sub ij and I transpose that, I flip to A sub ji, but if I transpose that, I flip back to A sub ij, and as I was saying a second ago, we arrive back at the original matrix A. You can do a similar argument to say that if you take two matrices and add them together, and then compute the transpose, it's equivalent to if you transpose them first and then added the result. In other words, the transpose of a sum is the sum of the transposes. If we take A and scale it by lambda, what we'll do is distribute lambda to each of the coordinates of A. And then if we flip our matrix to take the transpose, all of the entries had lambda, but A sub ij flips to A sub ji, and we recognize this as lambda times A transpose. For exercises 4 and 5, we will assume that the matrix A is square, and I hope you recognize why that's necessary to do the computation in 4 and 5. So in particular, I wouldn't be able to add A and A transpose if A wasn't square, because dimensionally that computation wouldn't make sense. If you haven't had a chance to do exercises 4 and 5, go ahead and pause before I present the solutions. For exercise 4, we can use our conclusion from exercise 2. So to take the transpose of the sum, we will add their transposes. So that takes the form A transpose plus A, which is fine. But to make it look like how we started, I'm actually going to use the fact that matrix addition is commutative and write this as A plus A transpose. We'll see something similar in number 5. So again, using the result of number 2, and also actually the result of number 3, treating -1 like a scalar, we know the transpose of A minus A transpose is A transpose minus A. And again, that's fine, but if I factor -1 in front of this new expression, we can actually write it as -1 times A minus A transpose. And again, that makes us think back to how we started. So let's talk a little bit more about these two. So the expression A plus A transpose is a symmetric matrix in its own right. And similarly with number 5, we've shown that the expression A minus A transpose is a skew-symmetric matrix. So here's a follow-up exercise for you to pause and consider. I claim you can decompose any square n by n matrix into a symmetric component and a skew-symmetric component. So in other words, you can write A as the sum of two components. One is symmetric and one is skew-symmetric. Do you see how to do it? Here's the solution. If you look at the expressions in 4 and 5, we have A plus A transpose and A minus A transpose. If you add those together, the A transposes cancel out, and you would just have 2A. We want to solve for A, so we just need to divide by 2. What I'm going to do to write this out is I'm going to break up 2A into A plus A just to add in an intermediary step. And then we can both add and subtract A transpose so that we haven't actually done anything, but we're bringing in those forms at the top. This allows us to solve for A as A plus A transpose divided by 2 and A minus A transpose divided by 2. The first component is symmetric and the second is skew-symmetric. I hope you enjoyed this exercise on square matrices. We're going to wrap up this video by looking at vectors. Now, often you would learn about vectors before matrices, but I'm actually going to say, okay, we know what a matrix is. Let's think of a vector as a single column matrix. So in particular, you could say it's in the set R to the n times 1, but we'll just think of that as Rn. That's the set of column vectors with n entries. The convention is usually to write vectors using lowercase letters. I typically use X, Y, maybe Z, sometimes U, V, W, but usually lowercase. In typing, you can make your vectors bold-faced, and that's usually what I do when I'm typing. But when I'm writing, I almost always draw a little hat. It's possible that you'll see me write at some point just plain old X, and I hope that it's clear from the context, if you're thinking over the dimensions of what we're working with, that my intention is the vector X. Since vectors are single columns, we don't need two subscripts to denote their individual coordinates, we'll just use one. So the vector X in Rn has individual coordinates x1, x2 through xn. And that's the typical convention. So if you see vectors x and y without having it broken down for you, you always want to think of x as having the coordinates x1 through xn, and y as having, say, the coordinates y1 through yn. The 0 vector similarly doesn't need two subscripts, so we'll just say boldface 0 sub n is the n by 1 matrix consisting of all zeros, and again, you can think of that like the additive identity for Rn. Sometimes you'll be looking at an array which is a single row, and you can use the word vector there to describe a row, but it's better if you make precise that you are looking at a row vector. So if I just say the word vector, please imagine a column. If it makes sense dimensionally to organize the entries on a row, I will call that a row vector. And I will not think of it as living in Rn, but rather R to the 1 times n like I've indicated here. As you work through, say, the field of linear algebra, it does matter how you think of vectors. So do not treat column vectors and row vectors as equivalent and interchangeable. Always track your dimensions. Always think about how your entries are organized. Let me also introduce in some named famous vectors. So what I call the standard basis vectors, or which are sometimes called the canonical vectors, for Rn, are the vectors with a single 1 in one entry and zeros elsewhere. So E1 has a 1 in the first coordinate and the rest of the entries are 0. Likewise, E2 has a 1 in the second coordinate and the rest of the entries are 0. In fact, you can recognize these standard basis vectors as the columns of the n by n identity matrix. Because we are thinking of vectors as special matrices, the matrix operations that we've already seen will transfer over to vectors, meaning we have scalar multiplication and vector addition as before. So here it makes sense to do 5 times the vector -1, 6 pi minus 3 times the vector 3, 4, 0 to get the vector -14, 18, 5 pi. Scaling vectors and adding them together, by the way, this is called a linear combination of vectors. So if you have scalars a, b, and vectors x, y, a linear combination has the form ax plus by. We talked about scalar multiplication and addition of matrices. I want to also bring in this special vector operation, We call it a dot product, or more generally an inner product. You may also see the language scalar product. So the dot product of x and y only makes sense if they're from the same Rn. And what we do is we pairwise multiply their components and then add the products together. Specifically, we would compute x1, y1, and add to that x2, y2, and add to that all of the other pairings through xn, yn. And then this dot product notion leads directly to what you could think of as the magnitude or length of your vector. You can also call it the vector norm, for which we say the magnitude of the vector x is the square root of x dot x. I'll leave it to you to check that that square root will always exist. So that exercise you can do on your own. Let's wrap up with these exercises here. So for the first three, I would like for you to just identify the dimensions of each of the objects below. Take a moment to pause and work through that before I reveal the answers. For the first one, if I say x is in R5, we want to picture a column with 5 entries, so x is 5 by 1. The matrix A that I've given you here, this has 2 rows and 3 columns, so it's 2 by 3. And then if B transpose is a 3 by 7 matrix, the original matrix B must have been 7 by 3. Now take a moment to compute the vector operations in 4, 5, and 6. Number 4, if I take any vector x and dot it with the standard basis vector ei, what that's going to do is extract the ith element from x, because all of the other products will just be the entry in x times 0, and the only one that doesn't vanish is xi times 1. If we do ei dot ej, well, it depends. If I and j are actually the same index, it would be 1. Otherwise, it's 0. This answer actually comes up enough in math that it has a special name. So anytime it's the case that if indices I and j are the same, the answer is 1, otherwise it's 0, you can actually describe that with the Kronecker delta, delta sub ij. So that delta takes the value 1 when I and j are the same, otherwise that delta is 0. And then what is the magnitude of any of our standard basis vectors? They are all unit length vectors, so they all have a magnitude of 1. That wraps up this introductory lecture for our series on matrix multiplication. So what we will do in the next video is actually start multiplying matrices together. Thank you for your attention.